Okay, welcome to the first lecture in Unit 7. We're looking at a binary code here, which represents the word chemistry. The quote that we have is that everyone is in a hurry to be the one, but no one wants to be the zero that adds value to the one. So looking at our learning goals for this lecture, students will understand the role of products and reactants in a chemical reaction. Students will demonstrate or will use chemical symbols to express chemical reactions. Students will be able to write word equations from the descriptions of chemical reactions, and students will be able to write chemical equations from word equations. And so basically what this is meaning is we're basically essentially going to be looking at going from a paragraph or a scenario to a word equation, and then from a word equation to the chemical equation which we use in chemistry. So what we already know coming into this, the evidence for chemical changes, we learned this back in our chemical and physical change unit. We know that evidence for chemical change includes a change in state, a change in temperature, and normally a change in color. And the other thing that we know is that we should be able to go from sodium chloride and from that to the chemical formula of NaCl. So naming is very important when we get into writing chemical equations. Now, what we should have picked up from the lab, thinking about the lab, why all the work? To go from binary to Spanish and then to English. The reason why we do this is when we write chemical equations, we always take steps. And so chemical reactions have overwhelming number of variables. There's a ton of things going into it. And so what chemical reactions, we need to be able to keep them straight. And so in a chemical equation, what that does is it organizes information and it quantifies information. So it puts everything in a nice little neat place for us to find everything, and that's essentially what we were doing. We were going from binary to Spanish to English and getting more precise as we move along. Now, pieces of the chemical reactions that we need to know. We need to know what the reactants are, the products are, and then catalysts or inhibitors. Now, reactants are the original pieces of the puzzle, what we start with. One thing that we can put here and kind of make a note of is that the arrow always points to the product. Okay, so the product is what we finish with. Okay. It's what you have after the reaction takes place. So if the arrow always points to the product, then the reactant is on the other side of the arrow. So reactants would be over here, and then products would be over here. Okay, if the arrow was going this way, we'd have products and then reactants. And then we also have what we have are catalysts or inhibitors. They can speed up or slow down a chemical reaction, and those normally go right above the arrow. And what the arrow basically means, your arrow basically means that something's being produced. So looking at it in an actual chemical reaction, what we see here, remember arrow always points to product, so there's our arrow. Guess what? There's our product. Here's our reactants on the other side, and then we have some catalysts which are right near the arrow. And so that's what our chemical reaction is, and those are the pieces that make it up. So the other pieces of the puzzle are going to be chemical symbols. So we have our chemical symbols, which we get from the periodic table, and then we have symbols that we use in chemical equations. Now, the symbols in chemical equations are not just for our elements, not just things on the periodic table. They mean specific things. So if we have an arrow, it means yields or produces. Now, remember I told you that the arrow always points to the product. Well, this is an arrow that points both ways. So that's a reversible reaction, and that's what we say something is in equilibrium, meaning it can go back and forth. So if we see these, they go in the middle, and they tell us what direction the chemical reaction is going. After a chemical formula, so say we have NaCl, that's sodium chloride, it's table salt. If we have an S after that, it's a solid. If we have an L after that, it's a liquid. G after that is a gas. And the last one, AQ, so if we have AQ after it, that means it's aqueous or aqueous, and that means it's just dissolved in water. So if I have something that looks like this, that means that it's just salt water. If we have above the arrow, we can have a triangle, which means heat. The heat's added or necessary for the chemical reaction. Or we could have a chemical formula, which that would mean that it is a catalyst. And then other things that we can have in front of chemical formulas. So say we have our NaCl. We can have coefficients. So say we have a 2 in front of that NaCl. That 2 is called a coefficient, and that means how many moles of that substance we actually have. And so these are some key chemical symbols that we need to know going into the rest of this. Now, the other big piece when we're writing these out is writing the correct chemical formula. And something that we have to remember as we're going through this is Brinkelhoff. Brinclhof, Brinkelhoff. And these are binary, not binary, they are diatomic. And so therefore, when they exist by themselves, they exist bonded as 2. So when bromine is by itself, it exists as Pr2. When iodine exists by itself, it's I2. And so when they're by themselves, and this is a key thing here, because say we have something like sodium bromide, it's not by itself, so we do not put the 2 there. But if we just have bromine sitting around and bromine, then we have to have Br2, and they're diatomics. And it's something to remember as we go through and we write chemical equations, because diatomics can come up, and if we don't write it correctly, it messes everything up. Another way to remember the diatomics, we can think of 7 atoms starting at 7. So we start right here. We make a 7, all of those guys, and then we don't forget hydrogen. So 1, 2, 3, 4, 5, 6, 7. So 7 starting at 7, don't forget hydrogen. Remember those guys as we're going through chemical equations. So now looking at word equations. Words and chemical symbols can be used to show relationship. And essentially what it is, it's the chemical equation written out, but instead of writing the chemical formulas like we see down here, we just write the words. And it kind of just puts everything into place. It's kind of a starting place to begin with before we actually write everything out. So when we're actually looking at a chemical reaction and there's a big long paragraph, what we can do is we can write the word equation in its pieces. And what we can see here is that we have hydrogen gas is reacting with oxygen gas, and it produces dihydrogen monoxide liquid. And so this is our word equation, and we would start there before we write the chemical equations to make sure we have everything in the right spot. So let's look at an example. It says the scientist takes a piece of magnesium metal and heats it in a Bunsen burner. The strip of magnesium melts and produces the strip of magnesium metal produces large amounts of light. After the light is produced, the Bunsen burner is turned off. And so basically what that means is that it's a chemical reaction happening. And the magnesium continues to produce light until the metal is completely gone, leaving behind a white powder. Write a possible word equation based on the reaction. And so what we have is we have magnesium metal, so we would just put magnesium. And it's reacting with something in the air. Well, in this case, it's reacting with oxygen. So we put oxygen, and it produces, well, when magnesium and oxygen kind of go together, they produce magnesium oxide, and that's that white powder. And that would be our word equation that we have. Moving on to our next example, it says pure distilled water and potassium hydroxide, the catalyst, are placed in a beaker with a positive and negative wire. The wire is connected to an electrical source, and a gas forms on the end of the wires. Write the possible word equation. So what we have is we have good old H2O, so we just write water, or we could write dihydrogen monoxide. And it breaks up into its pieces using our potassium hydroxide. Now put potassium hydroxide above the arrow because it's a catalyst, and it breaks up into the two gases. What are the two things that make up water? Well, hydrogen and oxygen. And those would be our word equation there. Now, going from the word equation to the chemical equation. Chemical equations include quantitative as well as qualitative information, and all chemical equations must have the same number and types of molecules on each side of the arrow. This is looking at balancing chemical reactions, and we're going to get in that into the next section. But what we can see here is we have the word equation written here, and then underneath of it we have our chemical equation. So we can go from the word equation to our chemical equation. So let's jump into an example. So here's the one we just wrote out, our word equation: solid magnesium plus oxygen gas, and we have magnesium oxide. And so what we do is solid magnesium is just pure magnesium, so it's just Mg. Okay, oxygen gas, we put an S behind it because it's a solid. Oxygen gas. Remember, oxygen, anytime we write an element, we want to check, is it a part of Brinkelhoff? Well, oxygen is a part of Brinkelhoff. It's a diatomic, so when it's by itself, we put a 2. And since it's a gas, we put a G. And then we have an arrow with a triangle, and the triangle is because we added heat to it. And then we have magnesium oxide. Now, whenever we write a compound, we have to follow our rules for writing our equation, or our formula. So on this we have magnesium and we have oxygen. Now it's a ionic compound, so therefore we have to crisscross. So magnesium has a +2 oxidation number, oxygen has a -2 oxidation number. Since their oxidation numbers are the same, that means that we can go ahead and we can reduce them, and a 2 and a 2 reduces down to a 1 and a 1. And we crisscross those ones, and we get our formula of MgO. And so that would be our chemical equation. And we see that this is the same word equation that we wrote. We have liquid dihydrogen monoxide, that water, so we have H2O, and it's a liquid, so we go ahead and we put an L. With our catalyst of potassium hydroxide. So again, we have to write the formula for it, and potassium is going to be K. Hydroxide is a polyatomic, it's OH. And so our potassium is going to have a oxidation number of +1. And then our hydroxide has a -1. And we go here. And crisscross, and we get our KOH. And then we keep going, and we have hydrogen gas, and so it's just H, and it's a diatomic, so it's H2, and it's a gas, so we put the G, plus oxygen gas, it's O2 because it's a diatomic, it's part of Brinkelhoff, and we put a G as well.